Um, okay, everyone, and thanks for joining us on this latest edition of our lecture series on evidence models and explanation. We have with us today Professor Paul Humphreys from the University of Virginia. Professor Humphreys works on a number of different issues in philosophy, in metaphysics, philosophy of science, epistemology. He has done a lot of interesting work on related to the philosophy of computational science and artificial intelligence. And I think today we're going to hear something related to that, which is, I think, a kind of neglected and underappreciated area within philosophy of science. So it'd be very nice to hear more from you on that. The topic of his talk today is going to be on predictive failures in neural nets. So yeah, I won't keep you waiting much longer. Professor Humphreys, do you want to go ahead with your talk?
All right, well, thank you for that introduction. Just a practical question before we start.
Yeah.
How do you prefer to deal with questions? I mean, I'm perfectly happy with people asking questions during the talk, as long as maybe they just interject, or if you're keeping track of the chat function and can let me know. What would you prefer?
So usually we save questions for the end, because okay. I think on this format of a Zoom, it's easier to do it that way, to just have the questions towards the end. But since Professor Humphreys is okay with interjections, if you really have a pressing question or clarification that you'd like to ask, please just raise your hand in the participant window, and I'll maybe point it out. I'll keep track of it. But if possible, please save your questions for the end. I think the talk will go for around 45 minutes to an hour. What is that? Yeah, something along those lines. And then we'll have about an hour afterwards for discussion. So please stay with us for the discussion. And yeah, so that's it.
Okay, all right. So thank you. I'm just going to start the slides.
Yeah, I think you're the host, so you can share your screen.
Yeah, that's right. So. All right. Can you see the slides?
Yes. Yes,
yeah. Okay. Yeah. All right. Good. So let me start by saying a little bit about how I got interested in this topic. As you probably know, I've had an interest in computational science for a long time. And that naturally led to an interest in neural nets and their use in artificial intelligence. And one of the striking features of contemporary neural nets, which have come to be called deep neural nets, is that despite their overall effectiveness, they sometimes fail in interesting and strange ways. And there's an active area called explanatory artificial intelligence, which is specifically targeting explanations for how deep neural nets achieve their successes and how they can try and ameliorate these failures. Now, the obvious way to approach the success of neural nets, because of their internal complexity, their non-linearity, and the current lack of understanding, is to perhaps apply some kind of reliabilist epistemology to neural nets. And I'm going to talk a little bit about that right now. And we'll see that the talk is about the degree to which reliabilism can and cannot be effective. And so here's the general definition, right? So this is a sort of core definition of reliabilism, which, if you have some background in epistemology, will know that to a large extent it's become the dominant approach to justification and knowledge in the last 30 years or so, largely starting with Alvin Goldman, but now there's an enormous literature on reliabilism. And of course, this core definition here is becoming encrusted with a number of quite subtle and nuanced modifications in order to take into account, increasingly strange counterexamples. But I want to keep the focus on this definition here, and let me just read it to you. So an individual S knows that P, and P is going to be a proposition here, if and only if P is true, S believes that P, so those are things brought over from older style epistemology, and here's the important thing, and a reliable process forms a belief that P, where P is a proposition, and a reliable belief producing process is one that produces a high proportion of true beliefs. And it's this last feature here that captures what the essence of reliabilism is trying to do. Reliabilism has, to a very large extent, wanted to get away from requiring further justifications for the reliabilist epistemology. So something called the JJ principle, which is that you have to have a justification for the reliabilist justification that you're giving, is largely rejected. And so the mere fact of having a highly reliable process, as long as you've got the belief and the truth, is sufficient for knowledge. And that's what that definition is attempting to capture. Now, here's, actually, before I go on to that, here's the central problem, which I'm going to use to set up the later discussion. So suppose you have a human epistemic agent, and I'll call him Roger, who overall has a very high reliability in recognizing an object as a cube. So you can give him objects of various shapes, and 95% of the time, he will recognize an object that is a cube as a cube, and therefore satisfies the condition for having a highly reliable belief-producing process. However, Roger is very unusual in the sense that in the 5% of cases in which he's wrong, he identifies cubes as being a hippopotamus. Right? Now, that is a radical and egregious error, but it allows the preservation of the highly reliable process. And the definition 1 will tell you that in the cases where Roger is presented with a cube, and as he ordinarily would, he believes that it's a cube, and he is highly reliable on identifying cubes. In these cases where Roger does actually have a cube in front of him, reliabilism will tell you that he knows that this is a cube. However, there's a fairly strongly held view, which reliabilism, as far as I know, has not taken into account, that the quantitative success of an epistemic agent needs to be balanced with how serious the errors that that agent is making. That if you have serious enough errors, this is going to start undermining your belief that that agent really does know what he or she is talking about. Now, let me address a couple of questions before we go on. I've given you the case of Roger with a 95% success rate. Well, you might say, well, that's not high enough. So let's suppose that Roger actually is successful at 99.9% of the time. So 1 in 1,000 times he makes the same bizarre mistake. Now, if it was simply a series of 1,000 trials and Roger made a mistake once, even though he believed that it was a hippopotamus, you might excuse him on the grounds that he had simply lost concentration or something like that. But if you have 1,000,000 trials, 1,000 repetitions of those 1,000 trials, and there's a very stable regularity that, although it's in each 1,000 set trial, Roger's failures are random, every 1,000 trials on average, he makes that same bizarre mistake each time. Now that's a statistically stable regularity, which seems to require some kind of explanation. And so I believe that the rate of failure in this example is not conceptually what is really at issue. It's the balance between the degree of success that you have and the degree of qualitative failure in the cases where the agent is unsuccessful. Now, one is also, I think, going to naturally gravitate towards issues concerning utility and pragmatism. In cases where, for example, an airline pilot occasionally mistakes a mountain for an airport, practically, that's such a serious mistake that we are going to require a much higher degree of reliabilism from the agent. But even with that utility consideration, the considerations that I just gave you, I think suggests that you can't use that to try and evaluate the epistemological issues here. So let's see what kind of ways we can approach this problem, and perhaps others will have occurred to you as you were listening to the statement. So the option is, that I've just given you, which is that radical errors can and do override otherwise high reliability in a process, suggests that that core definition of reliabilism needs to be modified in some way. So reliabilism in principle is fine, but in its current state, it's got to be modified. The second approach is to claim that despite what I've articulated in my explanation, to claim that in fact Roger does know in those cases where he has a true belief. But what's going on is that his underlying epistemic competence, which is a disposition, is being interfered with. And so you can appeal to the underlying competence in order to argue that even during those serious failures, Roger does in fact still know in some kind of dispositional way. And the third option is to say that, well, you've got a certain level of failure, 5%, 0.1%, or whatever it is. And our task is therefore to more precisely articulate what Roger's proper domain of competence is. If we can eliminate to a certain extent the cases that are causing the failures, then reliabilism can be applied to a more accurately defined set of cases. So those are the three options that I'm going to run through. And I'm going to spend quite a bit of time on the first option, and I'm going to embed it in the context of neural networks. Now, in order to do this, we need to shift from that traditional notion of reliabilism, which involves beliefs, so that we don't have to attribute beliefs to neural networks. And here's a stab at a modified definition, and I'll just let you read that without going through it. I, in general, is going to be a deep neural net. It could be some other kind of instrument which is providing a basis for knowledge, but we'll stick with the neural net case. I've put in there that the instrument has to contain an output representation because that's the kind of thing that a human agent is going to be interacting with. The truth condition is replaced by the requirement of an active representation of F, or just for details that it might entail the fact. And then this is based on the idea that deep neural nets contain representations. Now, again, there are people who deny this, but I think that I'd like to stay with that for a while because it makes the philosophical issues clearer. All right, now the rise of deep neural nets in the last, which can be pretty much precisely pinpointed as since 2011, when a number of technological and mathematical developments allowed an enormous increase in success of them. And I'm going to focus here, just for expository purposes, on image recognition, because it's much more accessible than a lot of other applications, and it fits with the motivating example of Roger. So here are a couple of examples in which machine learning actually outperforms humans. So we would like to use them as the basis of some parts of our epistemology. So in using machine-assisted diagnostic techniques for cancer, where you want to know somebody is susceptible to cancer, let's say you're looking at skin lesions, you want to know how likely it is a particular kind of cancer is going to recur in a patient, and you want to know how long their lifespan is likely to be. Using deep neural nets improved those predictions somewhere between 50 and 20% over just using physicians as far back as the early 2000s, and that was before the great leap forward in techniques. As you know, the discovery of the Higgs boson would not have been possible without the use of automated detection methods. 99% of the data that the Large Hadron Collider collects is thrown away before anything that resembles a human being has had a chance to look at it. There's just far too much data, and that selection process is done by deep neural nets. The detectors themselves were designed by neural nets, and that particular discovery would not have been possible without this modern kind of augmentation of human abilities. Now, I'm not going to go into a detailed explanation of deep neural nets, but there are a couple of things that I want to draw your attention to. And I believe that Don had circulated a paper by Cameron Buckner, which I think is a wonderful discussion of the differences between older style connectionist systems, which this diagram here is often used to illustrate, and the more contemporary approaches. This diagram, which you still often see, is misleading in at least two ways. First of all, there's only one hidden layer there, and the characteristic feature of deep neural nets is that there's at least two. What counts as deep is not precisely defined. You'll find neural nets of up to 1,000 hidden layers. Those are relatively unusual because they bring computational costs with them. But the kind of cases I'm going to be discussing maybe got 50 hidden layers. The second thing about this is, if you look at that diagram, you'll note that that neural net is fully connected. That is, every node is connected to every other node in the next layer. That's also unusual because, again, the computational burden of doing that in practice is far too high. So deep neural nets are frequently more sparsely connected than that diagram there. And here's a schematic diagram of what are called convolutional neural nets, which are the most successful in the area of image recognition. And you'll see that each so-called layer actually has a number of components that constitute it. So the input here on the left is an image of a car, and that's pixelated, and so the input is actually an array, n by m of pixels, which are colored. And the first layer, the convolutional layer, has a grid which slides over that array and picks out, let's say, a 3 by 3 subarray of the input. That then is put through a nonlinear processing, and then you get to the pooling layer, which is where you aggregate the information from the convolutions. So you will be, at this point, aggregating the information that is in, let's say, a 9x9 array down to a single point. And that's to identify what the dominant features in those 3x3 arrays are in each successive case. And then you then pass that on to the next layer, which has exactly the same kind of internal structure. And then you get to some technical areas until at the end here, you get to what's called a softmax classifier. And that's important because you can see there that there are a number of different classification categories that the neural net can identify. And that softmax classifier is a probabilistic classifier. So in this particular case, for example, it will give an output that this is a car with a degree of confidence of 91%. It might identify as a bicycle with a degree of confidence of 1% and so forth. So you've got a probability distribution over the outputs of those inputs. And that's where the 95% success rate comes from. You don't expect these things to be perfect because, as we know, human beings themselves are not perfect. So here's an example, and this is now going to, I hope, resonate a bit with the Roger example of the kinds of mistakes that even these highly successful image recognition devices are prone to. So you can take a neural net, which is very successful at identifying humans, monkeys, motorcycles, bicycles, guitars, and so forth. But when you juxtapose some of the elements, so on the left-hand side, you've got a monkey that's partly occluded by a motorcycle, that image will be identified in many successful neural nets as being an image of a human. Now, you can understand why it might do that. The images that they're trained on contain a number of different objects. It's rarely just a monkey in isolation. And the same thing with humans. And in that training set of what is often millions of images, it's going to be far more common to have a human in close proximity to a motorcycle than it is to have a monkey. So that kind of mistake is understandable. And the same thing with the second one, where you get the monkey also identified as a human. On the right-hand side, you get the inverse mistake. You superimpose a picture of a guitar over a monkey, and the monkey is then identified as a human. And interestingly, the guitar is identified as a bird, even though it really doesn't look anything like one. And the natural explanation for that is that the background of those images is a background of a jungle. You don't usually find guitars in jungles, but you do find birds, and that's probably the explanation for the mistake. But still, these are significant errors, and they need some kind of explanation. And just going back to the point that we shouldn't be too supercilious about our own abilities, here's a classic example of how the human visual system can be fooled by artificially developed kinds of images. I mean, I hope you can all see that there are actually a number of different images in there, each of which can be picked out by the human visual system, but as is true with most of these visual illusions, you have to flip back and forth between the two. So there may well be something like that going on with the artificial devices as well. Now, there's an industry that has developed over these mistakes around what are called adversarial examples. And here's an image which you may well have seen if you looked at the literature in this area. What this illustrates is that if you take, on the left-hand side, an image of a panda, and then you introduce into that pixelated array deliberately engineered noise, which is something around 1% of the information in the image. And so you amalgamate those two images, the one of the panda and the additional noise. What you get on the right-hand side is something which to humans, right, that thing on the right-hand side is the visual result of the amalgamation of the original panda image and the noise. You will all see that as an image of a panda. But to the otherwise successful image recognition device, that identifies that as a gibbon with something like 68% probability, which is, you know, a fairly radical failure. Now, people are worried about these adversarial examples because, as you can imagine, bad actors are able to exploit these. If, you know, we arrive in the era of autonomous vehicles, it's been shown that you can use similar techniques to mess around with traffic signs and fool autonomous vehicles into, for example, thinking that a stop sign is a yield sign and so forth, which of course would be a disaster. And, you know, foreign intelligence agencies and our own, I'm sure, are working on these kinds of issues. So those are interesting, but they are deliberately engineered. And I think it's worth looking at a case where machines make these mistakes on images that occur naturally. They're not like the guitar and monkey example. They're not like the panda and the noise example. So the most common database for image recognition is a database called ImageNet, which now has over 40 million images, most of which are scraped from the internet, but some of them are from other sources. And a subset of that, which is called ImageNet 1K, is a subset of the whole $40 million image database, which has 1,000 different categories. So it could be automobiles, it can be monkeys, it can be humans, it can be dogs, cats, and so forth. So there are 1,000 different categories in there. And a particular reasonably widely used 50-layer deep neural net, which is called ResNet 50 for the 50 layers, has a very high and well-established reliability on image recognition using that ImageNet 1K database. So with a set of naturally occurring images, the kind of things that you yourself would see on the internet, see in magazines and so forth, ResNet 50 is very, very successful. However, as I mentioned, otherwise highly successful image recognition devices are going to fail occasionally. And so a further subset called ImageNet A, which is a subset of ImageNet 1K, is selected, and it's deliberately selected, not in the sense that we're messing around with images, but we just pull out images on which ResNet has actually failed in a bad way. So this is the machine learning case that is parallel to Roger failing on recognizing cubes. You will pick out those images in which failures have occurred. And here is, here are a couple of cases in which you see what kinds of mistakes these machines would make, even though they're usually highly successful. I remind you that these images have not been interfered with in any way. They're naturally occurring. So a machine which we would all identify as a dragonfly identifies with 99% probability as a manhole cover. I think you can probably see why it might do that. If you look in the top right-hand corner, that looks like a dragonfly sitting on a placemat, sitting on an outdoor metal table. So it's possible that the machine has picked up on that fragment of the image and decided that this thing, even though the majority of the image is of a dragonfly, is actually a manhole cover. But that's still a bizarre mistake, I think, for a machine to have made. On the right-hand side, you have an image of a jaybird sitting in what looks like a window bird feeder. I think to all of us, it's clear what the subject matter of that image is, but for reasons that are at the moment not well understood, the ResNet 50 machine identified that as a Jeep. I mean, that's a really very strange mistake, and one that a reliabilist epistemology is going to have to come to grips with. So here's what I suggest as a possible amendment to reliabilism, to take into account, both the hypothetical case of Roger, which mainstream reliabilism I think needs to address, that's a conceptual issue, and also to try and see whether a modified kind of reliabilism within the area of deep neural nets could be an effective epistemology. So what we need to assess is this. Deep neural nets are evaluated on their probabilistic success. Remember, those softmax classifiers are probabilistic. So they're going to fail some of the time. But what we generally are willing to live with is when those failures, whether they're 5%, 1%, or whatever, are randomly distributed according to whatever probability distribution you think covers the category of images that are being examined. But what we don't want is when two images that fall within what we consider to be the same equivalence class, so these are both monkeys, these are both humans, these are both dragonflies, these are both jaybirds. If it's successful on one, it ought to be successful on the other. And if you think back to the Roger example, that's exactly what's peculiar about this. You've got 95 images of a cube, you've got a 96th image, which is clearly in the same equivalence class as the others, but yet it's classified in a radically different category. So we need to consider equivalence classes, and here's a suggestion that two instances of a category assigned to the same equivalence class, when the distance between them using some similarity metric that's widely accepted in the relevant epistemic community is below an agreed upon threshold level. Now, in everyday visual recognition, we do have a similarity metric. It's not quantitative, but it's widely agreed upon. In the image recognition community, there are also widely agreed upon quantitative metrics, which put images and in a number of other DNN applications, similar metrics are used, which assign things to the same equivalence class. Now, interestingly, those equivalence classes do not always completely coincide with human equivalence classes, although within what's called supervised learning, where the training process forces a machine to produce results that coincide with ones that humans would have had, then there's a significant degree of overlap between the human and the machine case. But this is the notion of being in the same equivalence class. So here's what I suggest as a modified definition. The part of it in small print is carried over in exactly the same way from the original definition of reliabilism. The larger type is the modification. So a reliable representation, sorry, part of my screen is blocked out by, okay, let me reduce this. Okay, so a reliable representation producing process, P, is one that produces a high proportion of accurate output representations, right? So that's where the high reliability comes from. And secondly, and this is really the new part, it's such that if you take the function that connects the inputs to the outputs of the machine, then there's no input to the process such that the output representation is farther from some agreed upon value, delta, from an accurate representation of the input, where delta is decided upon in terms of excluding egregious errors. So you look what you can live with in terms of the kinds of mistakes that you're willing to live with. You explicitly want to exclude these bizarre and radical errors that Roger and the Dragonfly and the Jeep examples introduced into the picture. And once you've done that, that allows the definition of reliabilism now to be immune from the problems. So that's the part that specifically is concerned with reliabilism and its relation to deep neural nets. So I hope you can see that there is an interesting interplay here between some mainstream issues in epistemology and some of these very interesting developments in artificial intelligence. All right, now I'm going to spend the rest of the talk on working up to options 2 and 3, if you remember from the beginning. We've dealt now with option 1. And I'm going to introduce a couple of types of explanation, which, although they've been lurking in the background in the philosophy of science literature, I think haven't been highlighted in the way that perhaps it would be useful to do. So what I call a prediction explanation request has the standard form. Why has a method been predictably successful on some task? And we're all familiar as philosophers of science with a very famous example of something, although it's not called that, is in fact a prediction explanation question. And that is the question of scientific realism. Why is science overall, as a method, predictably successful? And of course, there are many, many different answers that are given to that request for a prediction explanation. And scientific realism is the one that, of course, realists think is needed in order to get some satisfactory answer to the prediction explanation request. Anti-realists, generally speaking, want to dismiss the request for explanation in a way that, speaking as a realist, I think is actually not warranted. Now, scientific realism, and many of you probably are on one side of this, many of you are on the other. Generally speaking, scientific realists are either selective scientific realists or sort of global scientific realists. Now, I don't think global scientific realism, that is where realism about the domain is the uniform basis for a reply to a prediction explanation request. I don't think that position is defensible. You have to be, I think, a selective scientific realist. And one reason is that there are explanations for the success of parts of science which do not rest on scientific realism. And here's a well-known example. I hope you're all familiar with the example from ancient Greek philosophy of the Ptolemaic method for predicting the motions of the planets that were known at the time, based on a geocentric astronomical system. On the left there, you've got a diagram of a somewhat simple case of deference and epicycles. You've got the center of the epicycle moving in along the perimeter of the large circle, which was called the deferent. The epicycle itself is rotating with a particular speed and direction around its center, which is labeled there K, and then the red image, part of the image, is a second epicycle, which is doing similar things, except it's now centered on the periphery of the first epicycle. And as I'm sure you know, certainly within the limits of naked eye astronomy, which is all that was available back then, the deferent and epicycle method was amazingly successful. And the interesting thing about that is that there's a principal reason for that. And it transcends the fact that the ancient Greeks were limited to naked eye observations. It's a fact about that mathematical representational apparatus that, given enough computational power, given enough epicycles, it could have continued to be successful to an arbitrary degree of accuracy. And the result that lies behind that, this is one version of it, I'll give you there if you're interested in the mathematics. Just absorb that. If you're not, the essential feature about this result is that that particular mathematical method is capable of reproducing with arbitrarily close accuracy any reasonably well-behaved function. And so, given that the trajectories of the planets are describable by functions, they are in fact very well behaved, as Kepler discovered, modulo a few errors. And so the Ptolemaic astronomers could have continued to use a radically false representational apparatus while still achieving quite remarkable degrees of reliability on that process. So that's a reason to think that you don't have to be a realist in order to be a reliabilist. Now, interestingly, there are similar kinds of explanations that can be given within the realm of deep neural nets. There are analogous results which explain why these neural nets are so successful when they've been properly trained. So again, there are a couple of mathematical results there, which are, for those of you who are interested in the technicalities, and they say essentially the same thing, although using a different underlying apparatus. With, the sigmoidal functions are the nonlinear aspects of the deep neural nets. And as long as you've got weighted sums of those and you've got the convolutional parts of it, then again, you can arbitrarily closely approximate any reasonably well-behaved mathematical function. So that explains why, in a certain sense, these deep neural nets are successful. And what you've got there is a minimalist explanation that is purely mathematical, is non-realistic, and would seem to satisfy the kind of things that philosophical reliabilists always wanted. Right? You don't need a heavy-duty justification for the success of the reliability in a reliabilistic approach. You've got, in fact, an a priori, necessarily true explanation for why that reliability is going to occur. So I think, given what we've had before, you can stay within the general motivational orientation of a reliabilist program by using these mathematical results and getting a minimalist basis for the reliability. Now, that's fine, except that we're not quite where we need to be, because what the deep neural nets do is, given a training basis, and that could be millions of images, as I mentioned, the training process fits that function to the degree of accuracy that's required to that training set. Once you move on to images or whatever it is that you want to make predictions on that are not in the original training set, you've moved outside the database, you would have to fit a new function to that extended data set. Now, the likelihood is that if you don't extend the data set too much, the original function is going to work reasonably well. But it does account for why you get these strange failures, that you've got a remarkable degree of fit on the original data set, but when you move outside it, you have an inductive problem. And the inductive problem, and this is why to us philosophers induction is so important, you may actually get failures which those mathematical results are not going to help you with, unless you want to retrain the system. And perhaps one reason why the Ptolemaic system would have continued to be successful, whereas in fact we see these failures in image recognition, is just that planetary motions are far stabler than the enormous heterogeneous variety of images that you get out there. The deep neural nets are far more complicated than the relatively simple epicyclic systems and so forth. So although the Greeks were pretty successful, you can't assume that those mathematical results are going to give you the stability in these enormously complicated and otherwise successful applications. So we get sort of towards what a reliabilist wants, but unless a reliabilist can address that inductive failure example, then I don't think that they've completely escaped the need for a justification or an explanation of the reliabilist justification. So that is not going to be, I think, a fully satisfactory reliabilist project. We just looked at prediction explanations. Here is the inverse of this predictive failure explanation. And they run like, why does method M, which is otherwise predictably successful, occasionally fail on some task? And we've seen a couple of examples of that already. And the special case we've been looking at, why does this deep neural net, which has been predictably successful overall, sometimes fail in surprising ways? So what we're actually looking for is a particular type of explanation, which I think has not been much discussed in the philosophy of science literature, which is a predictive failure explanation. Now, here's where we get into option 2. Here's a potential prediction explanation failure. So in going back to the case of Roger, because the situation in the DNN is sufficiently underdeveloped at the moment that I don't think it will be particularly informative. So let's sort of keep with what we can get a good grip on, which is Roger. Option 2, as you remember, is that Roger actually has developed a highly effective competence in a particular type of image recognition. But in some of the cases, his competence is subverted by some other mechanism. And our task is to try and understand what is subverting that mechanism. So, hypothetically, right, so we're back into straightforward philosophy here. Maybe Roger sometimes is randomly suffering from episodes of dementia, and there are certain types of dementia which result in very strange visual illusions, in which to him a cube does in fact look just like a hippopotamus does to the rest of this. Now, if that's what is going on with Roger, you would have an explanation for his failures, and that's what option 2 is asking for. However, there isn't in the deep neural net case available to us a minimalist answer to the prediction failure request in the way that we had the minimalist answer to the prediction explanation request, right? So granted that prediction explanations are left with the inductive generalization problem, the prediction failure situation is an even worse state, because we don't at the moment have something which is going to satisfy one of the core requirements that a reliabilist has, which is that you don't appeal to something like an underlying competence for the agent. It's a success-based or a performance-based explanation that we want, and not a competence-based explanation. So I think option 2, unless or until in the deep neural net cases, we have some kind of mathematical answer to the prediction failure case, the reliabilist approach is not going to give us what we want in the prediction failure case. Option 3, if you remember, and we're getting just at the end of the talk here, option 3 was to more precisely specify the domain of reliability of the otherwise reliable process. So suppose that we follow this option 3, and as I briefly described earlier in the lecture, we're successful in doing this, and we upgrade Roger's reliability on classifying cubes to 97%, leaving 3% of hippopotamus errors. Now, you can see here what the objection to option 3 is. If we grant that it's not only the degree of reliability of the process is important, but that's counterbalanced by the quantitative nature of the qualitative nature of certain radical failures. The only way that option 3 is going to work is going to be when you get to the limit value of Roger being infallible. As long as there are some qualitatively egregious failures that remain, conceptually, reliabilism, I think, is going to be forced back into option 1 with a modification of the definition. So here, just to summarize, are the conclusions, and I think we're pretty much on time here. First moral, reliabilism, whether you're considering the philosophical thought experiment of Roger, or whether you're looking at the serious, real applications in deep neural nets, it needs to take into account how egregious the failures of an otherwise reliable process are. And as far as I know, I don't think that that has yet been taken into account. We have 3 options. The first option is simply to modify the standard definition of what counts as a reliable process. And I gave you a candidate for that modification. I think it works pretty well so far, anyway. Second option is to try and explain away the failures. But if you want to do that, the explanations have to conform to what is the underlying motivation of reliabilism. And in the case of deep neural nets, the prediction failure explanations, what the explanations for those is currently an open problem. I mean, one hopes that, people will find a solution to that in the next 10 years or so, but that is not something on which anybody can venture a definite opinion. It's a surprisingly resistant problem in which there are at least half a dozen different views about what the correct way of approaching that problem is. The third option, as we've just seen, is that refining the domain of reliability is only going to work if the predictor is infallible, which is totally unrealistic because, as we saw in one of those slides, human beings are not infallible even in the realm of the visual. And the last suggestion I want to throw out here is that I think that despite the long-standing and very informative literature on induction in philosophy, not so much attention has been paid to why it is that induction fails in cases that it does. And I think that that area is one that potentially contains some very interesting philosophical problems. I mean, there is one famous one, that is, Goodman's GRU problem. You've got the perfectly well legitimated inductive inference that all emeralds are GRU. We all expect that to fail, and we have to give an explanation for why that is and why we prefer all emeralds are green as the inductive generalization as opposed to all emeralds are GRU. That's one case in which prediction failure has in fact been investigated. I think there are a number of other cases out there which maybe they're not quite as interesting as as Goodman's problem, but which certainly can provide us with some philosophical work to do. All right, so that's the end, and let me get out of the screen share and see if I can get back. And I'd be happy to answer questions. So thanks for listening.
Okay, thanks a lot, Professor Humphreys. That was a wonderful talk. I'm sure there are a lot of questions, thoughts, all of you have. So I'm going to open this up to discussion pretty soon. I just want to remind you that if you would like to ask a question or make a comment, please use the raise hand function on Zoom. If you're not sure how to access that, you go to the participant list, which you can access at the bottom of your Zoom screen. And then on the participant list at the bottom, you should see a button saying raise hand. Click on that and you raise your hand. I'll come to you in the order in which your hand is raised. And the other thing I would like you to keep in mind is that please just ask one question at a time, because I'm sure there's many people who are interested in asking questions. If you have a second question, you can raise your hand again and I'll cycle back to you once I'm done with the questions that are there. And just one small addition before I start taking questions. For those of you who are new or who aren't aware of this, we have a website for our ongoing lecture series, which I've linked in the chat. On this website, you can sign up for a mailing list where we send out announcements for future lectures. You can also see videos of past lectures. So if you haven't yet checked out our website, please do so. Okay, with that said, let's go to the questions. Prashanta, you have a question? Please unmute your mic, Prashanta.
Can you hear me, Tarun?
Yeah, go ahead. Yeah.
Professor Humphreys, this is an undergraduate level question. We teach to a student, and please correct me, what would be the difference between that? So there is a long problem about explanation when the probability is low. The example is that, we are spraying with germicide in my backyard, 92% or 93% died, some of them survived. So if we keep repeating it, we can get some sort of probabilistic prediction. Is your predictive failures are connected in that way? You said not much work has been done on that area.
Mm-hmm. Yeah, that's a very nice question. In an earlier part of my career, I was very interested in those kinds of explanatory questions that involve low probabilities. And as you know, the field developed a number of different approaches to that. And so let's just mention the one that's associated with Wesley Salmon and the use of statistically or probabilistically relevant factors. And that's the one that was built into your question. And the aim there was to find relevant factors and arrive at either a higher degree of probability for the explanation, or to arrive at the correct degree of probability. Now, that approach works if you're dealing with cases where what's called the correct degree of probability is the true one. And what that means, if you are inclined towards an objective physical account of probability, is that the system's got to be indeterministic, because otherwise it's an epistemically based probability value, and you haven't finished the search for statistically relevant factors yet. So the option 3 that I mentioned during the talk is really, I think, me reverting to an earlier stage of my philosophical interests and bringing to bear the use of statistically relevant factors. And I think, just to draw out one of the nice consequences of your question, is that back then, I don't think any of us thought about the question of, does it make a difference if the cases in which the explanation doesn't work are so different from the cases where it does. And perhaps there's something in there that would be worth revisiting the literature on probabilistic explanation. But you're absolutely right. there's an overlap between the two areas.
Thank you very much, Professor Humphreys.
Thanks, Prashanta. Jyoti, you have a question?
Hello. In computer vision or image recognition that uses convolutional neural network, we have much better results now due to large data sets that are available. Despite that, if random failure occurs, why inadequate regularization, overfitting, or a case-by-case study of a failure is not a good enough explanation for overall failure of a successful DNN?
Sorry, the last part of the question is, why are those regularization and other techniques not a satisfactory explanation?
For the overall failure of deep neural net.
Well, yes. Well, here's maybe I will put the question a little bit differently, and please correct me if you think this is not the right way to put it. So what are called regularization methods, for those of you who are not familiar with the term, are various ways of trying to control for overfitting. Now, overfitting, if you remember, is the situation where you have a set of data points and the method that you're using fits the function exactly to those data points without taking into account the fact that there is noise in the observation or whatever you want to call statistical irregularities. And one of the things that everybody works in this area is aware of is that deep neural nets are such powerful function fitting devices that it's essential to control for that overfitting problem, because if you don't, you'll get exactly that inductive generalization problem that I mentioned during the talk. So there are various ways of doing this. It's called dropout. So you occasionally, sort of take out or inactivate various nodes in the neural net and see whether the network is overly dependent on that particular node and so forth. So yes, those methods are very widely employed, but they don't provide an explanation. They're an attempt to, if you like, rectify the overfitting problem, but they don't explain why, even when highly widely used regularization techniques of that kind have been applied, you still get these bizarre failures. Did that address your question?
Yeah, it's like these regularization techniques work, but still they sort of fail to address the overall predictive failures of DNN, isn't it?
Yeah, that's right. And when I said that these issues are still an open problem, if you just sort of do you work in image recognition?
Well, I have a background of computer science and engineering, and
Yeah.
since AI is this new technology,
Mm-hmm.
it's just taking over. So I have been studying it.
Aha. Okay, great. Well, you've got enough background. If you do a quick literature search in this area, you'll find that there are 4, 5, 6 quite different explanations for what's going wrong in the kinds of cases that I explained to you. There are some who think that despite the antidotes to overfitting, these devices are still just memorizing the data set. And when you get an image of a dragonfly that's got that slight anomaly in the top right-hand corner, it simply doesn't recognize it, and its competence is irrelevant in that particular case. There are others who think that what is going on is that it's not the whole neural net that's being used in identifying a particular image, but localized areas. And people have tested this by mapping the activation functions in a particular area back onto the input space and seeing that there are sort of stylized and somewhat distorted representations of images that look like an image of a dog or something like that. So there is this spectrum of approaches to try and solve this problem, because it is a very serious problem, especially to defense and intelligence agencies. But I think it is correct to say that there isn't a uniformly agreed upon solution to it. So thanks for raising that. And I didn't say it during the talk because it would have been a little bit of a diversion.
Thank you. Thank you.
Okay. Thanks, Jyoti. Don, go ahead.
Yeah. Hi, Professor Humphreys. Thank you for that wonderful talk. I guess, I have a few questions, but I'll come to my later questions in the second round, but especially from epistemology. But from your talk itself, there was one thing which was slightly puzzling, because you set up a dilemma by saying that, look, we need to explain the predictive success. So what the DNNs do is they come up with good approximate functions. But the first horn of the dilemma is like, look, they just, because the approximate functions, they face this problem of inductive generalization. And then you say, look, the other horn of the dilemma is, look, if you look at the details, then that would amount to explaining the output, which is what you're saying, look, that's not what we are asking. We are not asking that question of how is it that the, what dials changed, which produced this particular output, right? No, first of all, I think that is how you presented the dilemma, but if that is true, and if I look at the second horn, it seems like one could, and here I'm referring to Buckner, who uses this notion of mathematical efficiency. But he refers to things like, what explains the success of DNNs is because of its depth. So if I understood him correctly, he says, look, mathematical efficiency, sometimes he calls it computational efficiency also, can be derived from all those different factors like sparse connectivity, the depth, max pooling, all those different techniques. Right. So it seems like one could at least try and say, look, I'm going to explain the predictive success of the task, the thing that you're trying to seek an explanation for, in terms of this property of efficiency, which is not necessarily something to do with a particular instance of an input-output process. Would that work? I was just thinking.
Okay. Yeah. So that's that's an important issue in evaluating what you want from prediction explanations and prediction failure explanations. So as you've noted, you could go in either of two directions. One is to say that what we want is a general explanation for failure. So, it doesn't recognize a dragonfly, it doesn't recognize a jaybird. What we want is a uniform explanation for those two and pretty much every other failure that the deep neural net is exhibiting. The other direction you might go in is to say that that kind of general explanation is not going to be available, and that there are specifics about the internal structure of a trained neural network, which you're going to have to appeal to in conjunction with specifics of the input in order to explain why it failed on the dragonfly, and then have a different explanation for why it failed on the jaybird. Now, all I can do is present those as two possible routes. Which of them is true, which of them is more effective. As I say, I don't think everybody knows right now, but it does reflect the difference in outlook in philosophy of science, which, you know, is familiar to us, between unificationists who insist that explanatory power is gained from providing unified explanations. So that's a general case. As opposed to others, which include me, who think that you just can't presuppose and you're not guaranteed to get unified explanations. And sometimes there are going to be individual explanations. So it depends on the details of the case, and that can't be generalized. Does that? See, they're two distinct possibilities, and they're distinct because, you know, logically, just if you had individual explanations for each failure case, if you just conjoined them, that wouldn't give you the kind of unified explanation that the unificationists want. So, you know, logically, they're different strategies. And I'm not sure that one can decide these questions on a sort of case-independent basis. It's going to depend on, you know, how these things work, depend on what the structure of the universe is, and so forth. What was that? I get the sense that that didn't quite answer what you were worried about.
Yeah, slightly. I mean, I guess, no, what I was looking for was, I mean, you're true. I mean, in that sense, the answer you just gave me was a continuation of the earlier question, which is, yeah, if you go for a case-by-case evaluation, I mean, that has its own pitfalls. Because in a sense, I saw this analogy that, you know, whoever is asking for a fine-grained explanation in terms of, you know, what happens within the neural network and not so much at the general level, is more like the mechanist who's asking for, you know, the component parts of the explanation in a phenomena. But it's a general area. That's why I said it's just an analogy. And if at all if I were to sort of, you know, be creative and say, take forward that analogy, I was thinking, how would I, to answer the why question that you're posing, which is explain why is it that this method is predictively successful. So in a way, you're not looking for those particular instances where the phenomenon occurs, where you're looking for those generalizations, a mechanist would say. So analogous to those generalizations, would we have those features of the DNNs that one could appeal to?
Yeah, okay, good. No, I think now I understand better what you were trying to get at. And so I was told earlier that there are a number of people who work in philosophy of mind here. And so what your question brings out is this. It's putting it in a slightly different context than you did. Do we want an explanation at the representational level? So that's one reason why I chose an image recognition as an example, because it's very clear that representations are involved, you know, in various points in that. So do you want an explanation in terms of the internal representations that a deep neural net is using? It's obviously got an input representation, it's got an output representation, which is a probability distribution. Are we going to explain what's going on in terms of its internal representations? Or do you want a, you know, what David Marr called an implementation level explanation, which is maybe not quite what you would call a mechanical explanation, but it's one at a much finer grained level of detail, and which is going to probably, given that you haven't abstracted from the processing details, going to be less likely to lead you to a uniform or unified explanation. Now, you know, those are again live issues. I mean, there are people both within philosophy and within artificial intelligence who believe that there are no internal representations in deep neural nets, and that you don't need them in order to get an effective understanding of what's going on. Others, of course, and this is, I guess, a dominant tradition in areas of philosophy that have descended from philosophy of mind, that representations are crucial. And you can't make any sense of these as being intelligent artifacts unless you've actually said something really quite contentful about those. So yeah, those issues are not quite all running in the same direction, but they're in the same kind of domain.
Okay, thank you, Don. Anuj Sirohi, please go ahead with your question.
Hello, sir.
Hi.
So, sir, my background is mathematics, and I'm working as a physicist in the direction of machine learning. So, my question is in this very sequence of predicting error of the neural networks, deep neural networks. So, what we do is that there are the two parts when we train a neural network. One is training part, when we have a deep layers and we train it with some algorithm. And another part is that pre-processing part, where we put input to the neural network. So when it gives error, in more often in the case of image processing, what we do is try to squeeze the training part, means try to adjust the weight through the regularization, etc. And we sometimes don't do much on the pre-processing part, means the representation part of the data. So sometimes it picks an image, some portion of the image, and it predicts something. And if it is a snow, then it will predict something. And if you put dog also, then it will again predict wolf. So basically, what happens is like that the representation part, the input part of the neural network, which is completely untouched during the inspections of the error of the predictions of the neural network. So do you think that these inability or difficulty of explaining the epistemological consistencies of the neural network or machine learning methods lies in the representation part, because the training part mathematically can be proven that you can fit up to the infinite precision, you can fit it. That is mathematically proven. So there is no epistemological problem out there. But in the part of representation, what the physicists do, they do not believe on these inputs directly. They try to construct descriptors. Those are physically meaningful, and then they get very, very, very accurate results. And they don't get very accurate results when they fit raw input directly. But when they pre-process this input in a meaningful descriptor, then they get very, very good results. So my question is, do you think these epistemological bottleneck of machine learning process lies in the representation or in training part? What do you say?
Yeah, very nice. I would say both, right? And you're right that I implicitly was sort of focusing on the training process and its effects. Sorry, that's.
Yeah, sorry about that. Yeah, go ahead.
Right. So yes, here's a rather brief response to your point. these methods, generally speaking, are needed to be applied to data that is drawn from uncontrolled circumstances. Do you agree?
Yeah.
So, although, yes, one can improve the performance of these things by, just even elementary methods like isolating which objects in an image you want the machine to focus on in the identification process. The application in the real world is not necessarily going to be amenable to those pre-processing methods that you've used. So as you know, since you work in machine learning, the problem of occluded objects, that is where only part of an object is visible in the image because there are other objects that are between it and the, let's say, the detecting device. Those are really, as you know, serious problems. And do you think that pre-processing is in some way inherently capable of dealing with that problem?
I don't have idea about it.
Yeah, I think as a practitioner, you might want to dig around in the literature to see what has been done along those lines. I agree with you that that there is a lot of work and work to come that can improve things further. But if you remember, I drew the distinction between the application of those mathematical results to planetary orbits, which are pretty noise-free. Right? I mean, one of the interesting things about astronomy is that although it's not experimental science, a lot of planets behave very much as though they're in a laboratory. Certainly not true with image recognition, audio recognition, and many other things. So I think that I want to emphasize, by the way, that this wasn't a criticism of the research projects there. I mean, their achievements have been enormously successful. I was just trying to isolate an issue that for philosophers is recognizable and I think needs to be addressed within the field of machine learning and artificial intelligence in ways in which there are a number of different possible answers. So anyway, thanks for that question.
Thank you.
Okay, thanks, Anuj. Anand, you have a question? Please go ahead.
Yes, thanks, Dr. Tarun. Thank you, Professor Humphreys. It was a very nice talk. My own background is basically, I'm a software engineer with experience with machine learning. And for me, it's interesting to hear this from a philosopher's point of view, coming from that angle. And what I wanted to respond to or ask about is I want to overlay this concept of a reliable process with an example that you yourself gave of optical illusions, meaning the human perceptual system suffers from optical illusions. So my sort of questions run along these lines. One, why is it not an option 4 to say that Roger suffered from an optical illusion and that explains the failure? And if that is reasonable, then why is deep learning different from the sort of reliable processes that humans are endowed with? Meaning, is that any different? I don't know if that question is clear.
Well, yeah. The immediate thing that strikes me about that suggestion regarding Roger is that it has moved pretty quickly into the domain of what I would think is an ad hoc explanation. Now, okay, so, you know, this is a thought experiment, right? I made up the example. So, you know, what the facts are is something that is different from in the neural net case. But if one simply says, well, all right, whenever he makes a mistake of this kind, he's suffering from an optical illusion, that's simply, by fiat, preventing those cases from serving as a counterexample to reliabilism, isn't it?
My thing is sort of the following, like I'm just, it's partly to do with maybe being in this field, I tend to partly model the human brain as well. Sometimes you model machines on humans and then you sort of take a machine model and apply it back to the brain. And my sense is that humans make mistakes in the same way, and this is no different, meaning you have homonyms, you have metamers, meaning there are these things that confuse us, like two things with a similar impact on us. And so in that way, there is no satisfactory explanation beyond, as you say, an ad hoc explanation. And understanding it even further will require us to decode the deep neural network. For example, to explain metamers, like maybe you might look at how the human visual system works, and after deep understanding of that, then you might be able to sift out and say, okay, this is the reason one gets confused between this color and that color, or something like that. And similarly, when a deep neural network, you added some noise to it and the panda became a gibbon. Of course, we don't understand why that pattern of noise leads to an illusion. But in a sense, that would require understanding the perceptual process of neural network, which is as hard as understanding a human, is basically what I'm getting at. It's no different from a human's perceptual system, which admittedly is a simplification, meaning like I'm sort of applying the machine back to the human. Yeah, but that's sort of what I felt.
Ah, okay, all right, wow. There's a lot of really interesting issues packed into that question. I noticed on the chat function, a number of people were suggesting that, you know, because they're not illusions for us, as in the panda case, one's got to take that into account, and that's an important issue. So, because artificial intelligence, to a certain extent, and for sociological reasons, is a technologically oriented activity rather than one that is purely scientific, the performance of these kinds of devices is measured against how successful they are for purposes that human beings want to use them for. Now, what that means is, and again, you know, with respect to supervised learning, it's the machine has to perform in a way where the success criteria are decided by humans. Now, if one took, and don't misinterpret this, but if one took a more strictly scientific attitude, there's a fascinating issue there as to whether, for example, the categories that a machine uses or would be more effective in using are going to differ in interesting ways from the conceptual visual categories that human beings use. And so if one was thinking along the lines, is there a distinctive machine epistemology? Should we sever this tight connection between comparing how human cognition works with how artificial cognition works, and simply assess them on their individual merits? Now, without wanting to run on too long, that is something that is important with the panda-gibbon example. When I mentioned that that noise is deliberately engineered to produce that result, in some cases, what you've got is that the machine has divided up what's called the feature space, that is the basically the criteria on which classifications are made, in a way that doesn't coincide precisely with the way that human beings would do it. And that noise pushes the machine from, with the original image being located in one area of feature space, and it pushes it into a different area of feature space, which is close according to the machine criteria, but is quite different with according to human criteria. So there is an explanation there for how that artificially generated noise works, and that's how they can engineer it. Those things are not presently available with the natural cases, but absolutely great question. And it gets us to the heart of, should we be modeling our understanding or development of these devices on the human brain, or are they sui generis artifacts? That runs right back to the origins of artificial intelligence. My own view is that human cognition is interesting. It shouldn't necessarily be the yardstick against which we assess these things, but the technological applications, in a certain sense, almost require us to do that. So thanks very much for that question.
Thank you, Professor. That was a very nice response. Yeah, it's a very interesting area as well, and I'm sort of glad to hear about these things. Thank you so much.
Okay, thanks, Anand. M. Garrett?
Yeah, can you hear me?
You're very soft. Maybe move the mic closer.
Yeah, this is about as close as I can get.
Okay, all right. I guess we can try. Yeah.
I will try. So I am thinking about how explanation is very tightly involved into what use is. So it is humans who kind of come up with.
I'm sorry. It's.
Yeah. It's almost inaudible. It's very hard to make out.
I'll try again. I'm going to play with my microphone and try again.
Okay. All right. So we'll come back to you in a second and see if it's better. Ravi Singh.
Professor Humphreys, I would like to draw your attention to given the kind of framework that you have talked about for predictive failure, I was just saying if these same issues were to map to in human cases where we are talking of graded situations, for instance, cognitive biases. Some of them are inbuilt, like they're part of our constitutional nature. So persistence of perceptual illusions, for instance, which refuse to go away, despite our the old thing of modular systems and so on and so forth, as well as acquired cognitive biases. And the very good test cases for acquired cognitive biases are, for instance, in the area of mental health, for instance, that wherein a certain kind of a traumatic situation, even though it is not there, a cognitive mechanism of individuals continues to wrongly interpret the cues that are available in the environment. So I was just saying, if we were to sort of juxtapose the kind of framework that you have laid out for predictive failure, and when we juxtapose these concrete cognitive scenarios that we come across with respect to humans, how you look at that?
Yeah, very interesting. Yeah. But you're absolutely right. They're very important. We know from the psychological literature, I mean, just the sort of famous examples of Tversky and Kahneman and Gigerenzer and so forth, that humans do bring to bear, either for good or ill, various cognitive biases in their judgments. And there are ways of correcting for that in some cases, and it's much more difficult in others. In the machine case, it's now well established that there are algorithmic biases in things like decision methods for whether or not you're going to release a prisoner on parole. And in the machine learning cases, a very common source of bias is in the databases that you're using to train the machines. So there are famous cases of this where in image recognition, the database was heavily skewed towards unrepresentative samples from the population. And this leads to racial biases, for example, in recognition where, you know, these things sometimes make bizarre mistakes. And it's because the training database did not include enough images in that particular kind of classification for the machine to be reliable. Whereas it is highly reliable in cases where there are many, many training instances. So those biases are very important. And there is a sector of machine learning that is specifically dedicated to try and discover and eliminate those biases, some of which are quite subtle. So yes, again, it'd be a nice task to have a look at how human and machine biases differ, and in some cases, how they're similar. So yeah, epistemologically, that's very important. So thanks for raising that.
Thank you, Ravi Singh. M. Garrett, you want to try again? I don't know if you've...
Yeah.
Yeah, okay.
Is this... Yeah. Okay, yeah, I think it was my microphone. But anyways, so I'm thinking in real world scenarios, it's typically not a single model system that we're using or a sort of single set data situation that we're training with that is actually used ultimately to do predictions. And that we typically expect actually better performance to come if we do have well-designed maybe ensemble systems with many, many models making predictions, or systems that have multiple goals, which is kind of related to the adversarial examples you gave before. And I was wondering, since ultimately explanation often comes from the humans that are using these systems, how do we think about, in such multi-component settings, concepts like prediction and explanation in which we have a very discrete sort of action, like a discrete single prediction, or humans, we often think of explanations as being discretely chosen among alternatives, given that these predictions and components do not come in neatly distinct sets in such systems, and they can be kind of adaptive and very diverse in how they're essentially fitted or reached by the computer.
Oh, okay. Let me have a shot at answering your question, and please interrupt because I suspect I haven't fully grasped what the central point that you want addressed is. So yeah, ensembles are used in other areas of modeling. So a kind of well-known example is with climate models. You know, they want to look at more than one because the predictions of future temperature increases differ. And as you know, I mean, there's all kinds of problems with using ensembles as there are with using meta-analyses in statistical studies. Aren't you just blending together inferior with superior modeling projects? So that kind of approach is used. I mean, it's got its virtues, certainly. But if I understood what you were driving at with one part of your question, we also presumably don't want to do this in an indiscriminate way. We want to try and identify, use not the entire ensemble, but the predictive models which we think are best motivated and likely to be most successful. The second part of your question I thought I picked up on is that you may be asking or noting that there are pragmatic aspects to your explanations.
When we at least, when we sometimes think of explanations, we have this idea of having maybe a single narrative, and when we say this is how X works, there's an implicit assumption that we are also saying that this is how X works and not some other alternative explanation. Whereas very often in sort of like large systems, you have sometimes completely competing components of the system are how it reaches what the output is. The adversarial is a good example. Here you use the adversarial to show a failure of a system, but very often that's how the system itself reaches its sort of fitted state. And I was just wondering, how do we can see the prediction, but how can something like that, or in other cases, it can be arbitrarily different, but how can that be related back to the sort of forms of explanation that we typically think of, which are usually not competing and not necessarily contradictory and all these sorts of things?
Yeah, good. Right, so the answer to your question is going to depend crucially on whether one thinks, as von Fraassen does, that any explanation is essentially pragmatic, or whether you think that pragmatics are an important part of explanations, but they can be seen as secondary issues after a more, if you like, objective account of explanation has been developed. Now, the way that, I don't want to take a stance on that because, you can choose for yourself which of those you think is appropriate. But what I do think is actually very interesting about the point that you've raised is something that we discussed a little bit earlier in the discussion, and it's this. So when people talk about the pragmatics of explanation, it's always, of course, for entirely understandable traditional reasons, the agent who's requesting the explanation and the agent who's giving the explanation are human agents. Now, in explanatory AI, of course, that's not true. What explanatory AI in its current incarnation demands is that amongst other things, the machine itself provide a human user with an explanation of how it arrived at its result. So you've got an artificial intelligence agent providing an explanation, which has got to be adequate to a human being. And in the General Data Protection Act in Europe, that's now a legal requirement for a number of AI applications that they've got to be able to explain to humans how they arrived at their results. Is that going to always be true? Now, this is where we get into some really interesting ethical issues. Suppose that, and let's take a controversial example, image recognition systems on armed drones turn out to be better at detecting the presence of a terrorist than human beings are. Now, currently, and I think quite rightly, we don't let, or the appropriate agencies don't let machines override human judgments. It's always got to be approved by, at least as far as I know, maybe operationally, this isn't no longer true, but there's always got to be a human in the loop with those decisions. But that presumably leads to a decreased level of effectiveness on the part of those systems. So you're judging the moral issues here against, effectiveness. Those are absolutely legitimate discussions that have to be made, but they're inescapably about, do we defer in some cases to machine judgments, and we certainly do in the case of the Large Hadron Collider, or do we always want them to have to conform to the pragmatic interests of humans? Yeah, I can't give you an answer to that. I mean, it's a huge and important philosophical issue, but
yeah, but I can see how it makes explainable AI. Yeah, then it raises the question, what is the alignment between
exactly
the machine and human explanation?
Exactly, okay. And there are and there are going to be huge pressures to defer to the machine.
Okay.
In medicine, that's already there with the superior predictive abilities. The burden of proof now is really on the oncologist to argue that the machine is wrong. So yeah, it's going to be a very interesting next 50 years or so as we work out those
All right. Thank you. Darshi, you have a question?
Yes, Paul, greetings from Mumbai and to Charlottesville, I presume, where you are
Yes.
at with beautiful background. I was a Virginian for 9 years.
So, were you? Oh.
So, anyway, I have a sort of a historical comment. I will just read it because that's the best way I can put it forth, and I hope it is understood. In your first slide, you state reliabilism as the third condition in the analysis of knowing. I personally think that there is a defect in reliabilism as a condition because it seems to entail belief, whether you use forms of belief or causes as Goldman does. And this denies the logical autonomy of the condition. However, we can think of reliabilism dislodged from the analysis of knowing. And actually, I think this may work better for machine learning or machine knowing. Now, if we can analyze knowledge without belief, as John Hyman and others have done or do, then we would not be victimized by the begging the question against machine knowledge because machines cannot have beliefs. So this is my comment.
Yeah, well, thank you. Okay, so of course, you understand that there are many different things that go under the banner of reliabilism. I try to restrict myself to process reliabilism, so that's why the sort of onus was on the reliable process. And I tried to sidestep that issue that you mentioned about, providing an account of reliabilism that doesn't need beliefs, because that's so controversial in machines. So yeah, all those things that you said are correct, and I encourage you to develop, your own version of reliabilism that is tailored to this particular problem. Of course, it's difficult because epistemologists are always thinking about humans, and it's baked into the account usually that beliefs are there. But yes, I absolutely agree with you.
Okay, thank you.
Thank you.
Prakash? Prakash, are you there?
Yes. Yeah, okay, thank you. Professor Humphrey, thank you for this lecture. It was excellent. My concern is I'm looking at the domain of know-how, from the pragmatic sense, so my concerns are the understanding of failure could actually have some epistemic importance, like the way you are kind of calling for explanation of the failure. But I want to know if this concern is between what is the truth and what is knowledge. And in this case of reliability, you are, there is some idea of consistency that is also involved. So it's not something like, you know, the case where people could make this distinction between synchronic and diachronic kind of phenomena. So there is the possibility of learning that is missing in the discussion. My concern, my feeling is that failure may be more epistemically relevant in the learning process than success.
Yeah. I'm not sure I've quite caught what.
Okay, so I could rephrase in a slightly different manner. When you spoke about these the images, for example, the J and the Jeep.
Yeah.
That was a single instance, and if you could think in terms of what happens, whether you know, when you repeat, when that error occurs, does the same thing occur? That every time a J is you know, represented as a Jeep, so that doesn't have the same you know, the force, epistemic force, when otherwise you speak in terms of quantity and quality and competence and performance. You know, like when you're making this case that it's not just the probability of success that matters in this justification, but it's actually the quality when something egregious happens. So that seems to be your, the motivation for your, you know, the theory. So I was wondering if, what if you apply the numbers to failure? So it doesn't make the same sense, because if every time the mistake is that the J is always seen as Jeep, it's almost like the outliers you get in data sets. So you might need some other method to deal with it, maybe include it or maybe exclude it, that kind of thing. Maybe it's just a pragmatic thing, but I don't have a background in machine learning. But I was wondering what happens, what about the idea of learning over time?
Yeah, okay. So there are variations on the problem. I gave you the, in a way, the simplest one where, you know, Roger makes the same mistake every time. Now, you've introduced an interesting variant on this, which is, you know, if I understood you, you were suggesting that, well, right, in the machine case, it recognizes J as a Jeep in one case, but then it does something different and maybe also bizarre, but it's recognized, I don't know, let's say as a violin. Is that part of what you were asking about?
Yes, yeah.
Yeah.
I wanted your opinion on what would be the implications if you look at these two situations differently, because the idea of reliability is basically is concerned with risk and error, you know. So
yeah,
that point of view.
That's right. So both reliabilism and the assessment of machine learning methods are probabilistic. So you have to expect variation in the outcomes. And I mentioned very briefly that in the machine case, you know, as long as the errors occur randomly, then that's something that people are happy to live with. Well, what does random mean? It means that you have some knowledge about what the proper distribution that covers the instances you're applying the method to. And as long as the errors that you're making do not fall outside that distribution, that is, that if you put a statistical test on them, that they would fail with a very low probability according to that distribution. As long as you avoid that, then the fact that they're random is okay. So there's a territory in between the simple case that I gave you, where the failure is always of the same type, and cases that you introduced where the system is failing, but is failing in recognizably different ways, is there a way to decide within the general domain of reliabilism at what point one should start claiming that you've got to start addressing these qualitative issues as opposed to the quantitative ones? I suspect that one can do that. It will be a little bit complicated and maybe not as persuasive to philosophers as a simple case, but I think the considerations are similar.
Thank
you. Okay, thank you, Prakash. So I think we have time for one more question, and since I don't see any hands raised at the moment, let me ask a question that I had. So I'm not sure if I fully get the intuition that is driving this whole thing in the first place. The idea that if there's an egregious or bizarre error, then that indicates a problem for reliabilism that is ungood. In fact, I mean, especially when you extend reliabilism to instruments and don't just think of it as an analysis of knowledge, but of instruments as a knowledge base. In some cases, it seems like an instrument making bizarre errors is actually better for us when we're using it as a knowledge base than if it was making sort of errors that we can't really tell are errors, right? If Roger was categorizing things as cubes or spheres, and he occasionally categorized a cube as a hippopotamus, that's less of a concern than if he occasionally characterized this cube as a sphere, right? And so I guess, yeah, so I'm wondering why one would think, I guess, yeah, maybe this is just an invitation to maybe defend the intuition a little more, because to me, it just doesn't seem that compelling. Yeah.
Yeah, good. So the original example involving Roger is obviously appealing to a reaction about that example. And I think that the reaction I gave you is reasonable within ordinary epistemological circumstances. So think about you have somebody who is presenting himself as an art expert, right? And so, you know, he a lot of the time recognizes a Renoir as a Renoir and a Manet as a Manet and a Van Gogh as a Van Gogh and so forth. But against the claim that he's an expert at art, he also classifies occasionally a Rembrandt as a Picasso. Now, I'm really about as convinced as I am as a philosopher that one would start questioning the extent to which that individual really is an expert at art. There are, for example, I mean, there must be serious gaps in his knowledge which are being revealed by these strange mistakes and which one needs to address. In the same way, I think that if one has a student who in many ways is very good, let's say a philosophy student who's quite good at philosophy, but they show a disturbing degree of ignorance on the relative positions of Kant and Hume, one would say, yeah, he's pretty good, but you know, he doesn't know philosophy as well as he should.
I mean, I think isn't reliabilism meant to assess knowledge of particular propositions? So I mean, it seems to make sense for the art expert to say, okay, he knows that this is a Vermeer, say, but he doesn't know that that is a Rembrandt. I mean, the question of whether he knows art as a general category may be a separate question, but that doesn't seem like the kind of thing that reliabilism is meant to assess, right? Yeah.
So then, if you have that reaction, then I think you're going to initially head for the third option.
Okay.
You're going to say, is in fact, you know, I did as well. You said, you know, he's an expert on many areas of art, but not in this one. And, you know, say he's pretty good as a philosopher, but he doesn't know this area in a way that he should. So then the question is, do the concerns I raised about option 3 and the claim I made, and this is an important thing, you're right to bring it out, that almost regardless of the degree of reliability of the human or the machine, radical qualitative failures can undermine that. Is that correct? I do think that we're bringing to bear pragmatic issues on this and not purely epistemological, but there's a lot we could discuss about that. And you're right to raise that.
Okay, thank you very much. Unfortunately, we're out of time. I'm sure there are others who would have questions as well, but thanks for the lovely lecture and the great discussion afterwards. Thanks for being with us for so long. Thank you all who have stuck with us throughout this, and those of you who haven't stuck with us, thank you in absentia. And yeah, please join us next week if you're able, where we will have Professor Michael Strevens giving a talk. We'll send out an announcement about that soon. And so, yeah, thank you again, Professor Humphreys, for that great talk. And I'll see.
Yeah, and thank you and the audience. That was really great questions. Really, really nice. And I'm going to have to think about some of them, right. Which is nice. Thanks reward.
Okay.
Thanks, Paul.
Bye, everyone.
Thanks.
Okay. All right. Take care, everybody. Yeah. Stay safe. Bye-bye.